right here at the very top. So when we did inverses in the past, we switched the x and the y values. Now, we're going to use that idea here to first, we're going to talk about inverses of an exponential function here, okay? So you can pull out your calculator if you want. You can probably do this without a calculator too if you really thought hard. I want you to fill in the table here for f of x is 2 to the x. Okay, so we're going to put that into our calculator. Look at the table, fill in those values. Go ahead and take a second, work on your own there. And once you've filled in that table of values, I want you to plot the points. You know this is an exponential, so it should look like stuff that you've done before. Okay. So go ahead and just use your calculator here. I'm going to plot it up here as well while you're doing that. And then graph that function. We all agree that that's what your graph looks like. That graph we talked earlier in the unit has an asymptote. Where is the asymptote of that graph? Y equals 0. Okay, so that's the top. There's a box at the bottom. There's an asymptote there at y equals 0. Now this isn't on your paper, but let's review. What's the domain of that exponential function? Okay, negative infinity to infinity. What about the range? 0 to infinity, or all the y's greater than 0, right? Because there's an asymptote of the x-axis, you can't be negative. All right, now, we're going to graph its inverse. And we set up above that you graph an inverse by switching the x and the y values. So I want you to take a minute and take this table on the left and swap the x and y values. So all those x's, negative 2, negative 1, 0, those are going to become your y values over here. And all the y values are going to become your x values. And then after you swap those x and y values, that table is the ordered pairs for the inverse function. So I want you to take then a couple minutes and plot all those points as the inverse. So 1/4 negative 2, 1/2 negative 1, 1, 0, 2, 1. Go. You should have another graph. Mine's pink. So yours looks like a pink graph once you plot all the points. Now, as you're looking at that graph, does that graph have an asymptote? Where is it? At x equals 0. Well, that's a good thing because remember we said when we have an inverse, all the x and y things switch. So the asymptotes switch the x and the y. Does that graph look like any parent function you know? Kind of like, well, square root's a little bit, but what was the other graph that looked kind of like square root, but a little bit different? Log of x. Logarithm. That's what this is. We don't have the equation yet. We'll talk about that later. But that graph is a logarithm. So the inverse of this exponential is a logarithmic graph. So I told you we'd get to it eventually. So we have the logarithm there. Now, what equation, what line do all inverses reflect over? Y equals x. Okay, so graph that real quick. Let's just verify. I know you don't have a ruler. Just estimate where it is. But you know that we're going to reflect over y equals x here. Does it look like those two reflect over that line? Yeah. Okay. So it's all coming full circle. Now we have a logarithm, which I said was the inverse. Now we're going to skip the second graph. Do you trust me that the bottom one's going to look kind of like this? Yeah. Yes, I would trust me. Let's flip the page. Let's answer some questions about logarithms real quick and their graphs. So this is a really important thing to internalize, and I'm going to talk about it a lot the next couple days. The inverse of that exponential function is called the logarithm. Okay? Just like the inverse of the quadratic function was the square root, and linear function is inverse is linear. in exponentials is called a logarithm. Now, when I look at that graph that I just made, the pink one, we're looking at the pink one here. Is there a y-intercept for that pink graph? No, why not? Yeah, there's an asymptote at the y-axis, right? So we can fill that part in. So there's no y-intercept because there's an asymptote at x equals 0 for the y-axis. Right? It never touches it, there's no y-intercept. Was there an x-intercept? Where at? 1, 0. Okay, so there's an asymptote, or I'm sorry, an x-intercept at 1, 0. What's the general trend of the graph? Increasing, decreasing? It's increasing. Okay. And we talked about this a couple minutes ago. What do you think is the domain of that pink graph? 0 to infinity, or all the x's greater than 0. Right? You can write it two ways. Either 0 to infinity, or all those x's bigger than 0, because you can't be negative because there's that asymptote at 0. And what was the range? Negative infinity to infinity, all real numbers. Now, if we were to go back and do all those characteristics for the exponential, they're all opposite, right? So the range of the black graph here is from 0 to infinity, and its domain is all real numbers. So everything has swapped. So let's talk about what is this definition of a logarithm. We know that it's an inverse of an exponential, but the actual definition of a logarithm says if I'm given a exponential equation, y equals b to the x, here's what a logarithm is, the equation for it. You're going to write it as log. You're going to write the word log. Now, the next thing we're going to write is the base b, is what we're going to say. Now, the base is written as a subscript, which means it's a little b that's lower. So log, a little lower b. And we say of y, the y is on the same level as the log. It's a regular sized y. So log, low b of y equals x. That is the formal definition, an equivalent statement of a logarithm with its exponential. We're not going to do a ton with this. We're going to use this definition here. We're not going to do a ton with like the equation. You'll do that more when you get to pre-calculus. But for now, we just need to know the definition. So real quick, let's just do A here because we only did one graph. Let's write the equivalent logarithmic equation for that inverse that we just found. So I'll help you do it here. Let's rewrite f of x is 2 to the x. Let's rewrite it as y equals 2 to the x. And we'll start to see how these two logarithms and exponentials will work together. So the inverse equation for this graph, the one we graphed in pink. So we start with log. We're going to write it as a logarithm. Now, when I look at this equation, it says log base b. So if I look over at the definition here, b is the base of the exponential. What's the base of this exponential? 2. So log base 2, little 2, of y. Well, y is the same. Y is what you're equal to. So of y equals x. Now, do we typically write equations as x equals? No. And I wouldn't worry about it. We are not going to, I'm not going to have you write equations of logarithms. This, you can rewrite it as y equals. We just don't really have the tools for it, so there's nothing to worry about. I just want to show you how you could just quickly write the equivalent logarithmic form of graph. Okay? All right, let's talk more about the definition. Let's kind of just keep going here. So, logarithms and exponentials, they're inverses, they work together. So what we're going to do is we're going to take this exponential expression, 10 squared equals 100. Do you agree that that's a true statement? Yeah, I would. We're going to take that equation, or that expression, and write it as a logarithm. So we'll do one, I'll show you a shortcut after the first one. So we're going to do the same thing we just did with the equation. Log. Now, this one has numbers, so it doesn't have x and y's to follow. We take the base. What's the base of the exponential? 10. So log base 10. Now it says of y. Now if I look over here at the definition, y is what you're equal to. What's the y in this number? 100. So log base 10 of 100 equals x here. X is the exponent up there. What's the exponent? 2. That would be the logarithmic form of that expression. Now, let's notice a couple things. We should notice that 10 is the base. Right here, it's the base of both the logarithm and the exponential. So the bases stay the same. The other thing to notice is that this logarithm, this whole left side, is equal to 2, right? So the logarithm equals 2. What part of the expression over here is the 2? It's the exponent. So the logarithm is the exponent. That's going to be important to know. Now let me show you a little trick, a little shortcut here to going between exponential and logarithmic form. I call it the curly Q method. Okay? So if I'm going to start with 6 squared equals 36 and write it as a logarithm, I always start with the base. So you can put your pencil on the 6 there, that's the base. Your curly Q loops towards the 36, okay? And then ends at the exponent. So that, if you follow that curly Q, that's the order that you write the logarithm in. So you write log, you started with the 6, so that's the first number you write, log base 6. What was the next number you got to? Of 36 equals 2. You ended with the exponent. So if I do the same thing over here, I do my curly Q. Log, what number do I start with? Base 2 of 32 equals 5. Now we'll figure out why that's going to help us out later on. But one more thing, I just want to reiterate this because it's going to be helpful. You should notice the same pattern as above, that the answer for the logarithm was always what part of the expression? The exponent. Now, why do I keep saying that? Well, not tomorrow, but on Friday, we are going to use logarithms to help us solve other kinds of equations. And those equations are going to look something like this. Like 12 equals 6 times 3 to the x. Now, as of today, do you know how to get that x out of the exponent? No. We're going to end up using a logarithm to help us. We just still don't know how yet. But that's where this is going. So knowing that a logarithm is an exponent is going to help us out. All right? So we can go the other way now. I can write logarithms as exponential functions. Okay? And this is going to work too. So the curly Q helps here. I always start with the base. I loop around, so I write the 4 first, that's my base. I loop around to the equal sign. That 2, we said the logarithm, the answer is the exponent. So 4 to the second, and I loop into my 16. Is that a true statement? Yes. Yeah, 4 squared is 16. So this logarithm gives me the exponent for 2. So what's the next one if I follow the same pattern? 6 to the 0 equals 1. True statement. What's the last one here? 3 to the t equals n. Okay. So all we've done so far is use the definition of a logarithm to go between the two formulas. Okay. Now let's use it for some kind of purpose here. Let's solve some equations. We're going to solve a logarithmic equation. That means we start with a log. Now before we do that, let me ask you, this is not your paper, you don't have to write this down. Let me ask you a question. If I have something like this, x minus 5 equals 12. How do you solve this? You would add 5, right? Now, why would you add 5 here? Why don't you do something else? Because what? All right, you want to add 5 stuff, but why did you choose plus 5? Why didn't you do divided by or square root or something? Because it's the opposite, right? You have to do the opposite or the inverse operation to move the 5. Same kind of thing if you have x squared equals 9. In order to get x by itself, what was the inverse of squaring something? Square rooting. Okay, so what we've learned today is that what's the inverse of a logarithm? An exponential. So in order to solve a logarithm, you have to use its inverse function, which is an exponential. So what we're going to do is we're going to solve this by turning it first into an exponential, because that's its inverse. So let's use that curly Q, that definition we've been working with. So we take 9 to what power? X equals 81. Now, that one you should be able to look at. What's it's going to be? 2. All right, that's a simple one. Same kind of thing here. I take 8, and I make my curly Q. 8 to the third equals X. And what's 8 to the third? Oh, it's breaking my heart. 512. Oh. Put that on your quiz next week. No. No. Yay. Yay, that's a better answer. Well, how do we do this last one? 5 to the second equals 3x plus 1. All right. So how do I simplify this? 5 to the second is 25 equals 3x plus 1. I subtract the 1 and get 24. And when I divide by 3, what's x? 8. All right, simple. There are 3 right underneath. I want you to try those next 3 on your own. Try them in a minute. We'll check our answers here, okay? Do all these, but let's check. Let's see. D, you should have gotten 0. Yeah? 5 to the 6. Let's see if I remember this. 15,000, is it 625? Yeah. Good memory there. And then this one is 2. Do anybody have a question? All right, let's have our calculators. Let's do one more little thing here. There are 2 kinds of logarithms, actually. Right? We can't just have one, we have to have 2. The first one, excuse me, just spilled water everywhere, says logarithms that use 10 as the base. So that means you would write it as like log base 10 of something, right? 10 is the base. Those have a name. They are called a common logarithm. Now the reason it's called common is because they use log base 10 a lot. One thing that log base 10 would be used for is with like acidity and bases with pH. They do logarithms with that. So they use a common logarithm, log base 10. So the way we write it, instead, because it shows up so often, because it's common, instead of having to write log base 10 of something all the time, they shorten it to just be log of x. They don't put a base at all. So instead of writing log base 10 of x, they just write log of x. So if you see a logarithm and there's no base, you should assume that it's a 10. So what I want you to do here is type into your calculator log of 78. So your calculator will evaluate logs for you. If you don't know where the log button is, it's on the left over here. You type in log of 78. Now, I think Stephen has an Inspire. Does anyone else have an Inspire? Okay, on your calculator, you can still hit log of 78. When you hit log, it will give you a little box to type a subscript, right? If you want, you can either type log base 10, or you can skip over that box for log base 10, and it'll assume that you'd want base 10. So if you don't type a base, it'll assume it's a 10. So what's log of 78? Give me like 3 decimal places here. 892? So what is that telling us? Well, what that logarithm, that answer is actually telling you is, what's the base of this log again? 10. So what it's really saying, if you use that curly Q idea here, is that if I took 10 to the 1.892 power, I should get 78. So let's check. What's what's 10 to the 1.892 power? It's close, right? Why is it only close? Yeah, because we rounded the exponent. But would you agree that that's right? 10 to that power gives me 78? Cool. All right. Now, here's our second kind of logarithm. We've been working, or we learned the number e the other day. And so we have, it's hard to read, it's kind of small. We have a log base e of x. So e keeps coming back. This is on your paper. I'm just writing it bigger so you can see. Now, log base e is also very common, but the name common log is taken. So they decided to call this a natural logarithm. All right, we're going to use e a lot. Where did we see e already? And what kind of formula? continuous compounding interest. So E shows up a lot. So they said, okay, we're using 10 a lot, we're using E a lot, let's make a special kind of log for it. So they call it the natural logarithm, and there's a shorthand way of writing that as well. It is ln of x. Now, don't say ln x. That drives me nuts. It's not ln. It's like when in geometry when you did sine, cosine, and tangent, and people were like, oh, it's cos of 78. That drives me up wall. It's not cos, it's cosine. ln is for natural log. Log naturel. It's French. But it's natural logs of something. Oh, that's like nails on a chalkboard. Like say the whole word. Say the whole word. Sin, yes. Sin, tan, like just say the word.
Wait, where's the thing?
So the natural log button. So let's type into our calculators. Let's find the natural log of 26. It is actually, it doesn't look like a 1, but that's okay. It's actually right under the log button, ln, right underneath, next to the 4. So natural log of 126 here is 4.836. All right, now, again, let me just review with you. What does that mean? Well, what's the base of the natural log? E. So if we put that into an exponential, if we wrote that as e to the 4.836 power, I should get roughly 126, right? So let's see. What's e to the 4.836? It worked out, right? So that's what your calculator is doing when you type it in. It is looking for the exponent that you're raising the base to. Okay? So like this one's looking, your calculator just does it real fast, but it's saying, okay, e to what power gives me 126. That's what it does. All right, now, I'm going to skip this example 13. Let's do example 14 here real quick. So example 14, evaluate log of 10 and natural log of e. All right, so in your calculator, can you type in log of 10? What do you get? 1. Can you type in natural log of e? What do you get? Also 1. Why? Because what? We were just talking about with turning it into an, what's the base of this natural log, common log? 10. So that is saying 10 to the first equals 1, right? What's this saying if it as an exponential? E to the first equals e. So that's knowing those rules that natural log or log of 10 is 1 and natural log of e is 1 will help us starting on Friday. All right, it'll help you once in a while, but it is good to know. It'll be a shortcut for you to know those natural logs and logarithms. Okay? All right, we good? So here's what we're gonna do. I'm gonna have you come up. We're gonna grab a whiteboard, marker,